Hey everyone! Electronic components are the tiny building blocks of electronic circuits which make up circuit boards and all our electronic devices. If you want to learn how to design, repair or analyze electronic circuits, you absolutely have to be completely familiar with electronic components, their different types, and the characteristics of each one. In this video, I'm going to introduce you to 6 electronic components that are super useful and will really help you on your electronic learning journey. Oh, I almost forgot to say that this is part 4 of our basic components tutorial series, which is available in the basic components playlist right here on YouTube. In the previous 3 parts, I introduced 21 components, so I highly recommend you go check those out before watching this video. Also, we will be covering even more components in the future episodes, so please stick with me until the end of this video and until the end of this playlist. The first component we looked at in previous episodes was the resistor, this guy right here. If you remember, the resistor was the very first component in the first episode of this playlist, and in my opinion, it is the simplest of all electronic components. Now, I want to clarify that resistors don't just come in the shape we saw back then. They come in all sorts of different types and forms. In this video, we are going to explore and learn about some other types of resistors. So, without further ado, let's jump into the first one, component number 1, resistor arrays. Another form of resistor which consists of several resistors in a single package is called a resistor array. These components come in 2 main package types, through-hole like this and surface mount SMD like this. Basically, these components are just a bunch of regular resistors packed together into one unit. These are through-hole resistor arrays. They usually have one common pin and several pins from each of the internal resistors. The number of pins on these resistor arrays is usually an odd number, like 5 or 9 pins. A 5-pin resistor array consists of 4 internal resistors with 1 pin from each connected together and brought out to the common pin like this. There is usually a dot on the common pin to identify it, see? Like this, that here, or this one. The value of all these resistors is the same and it is indicated by the number written on the component. Look. This number is a 3-digit code where the last digit indicates the number of zeros. For example, if it says 472, it means we write the number 47 and add 2 zeros after it, which gives us 4700, meaning there are 4.7 kilo ohm resistors inside this array. Or, for example, this one that says 103 means we write 10 and add 3 zeros, resulting in 10,000, which means there are 10 kilo ohm resistors inside this array. Anyway, let me give you an example of how this component is used. Let's say you want to light up 8 LEDs in a circuit. You will definitely need 8 resistors, 1 for each LED. If you use a resistor array like this one, your circuit will be much neater and cleaner. There is another type of resistor array, the SMD type. For instance, this component you see here is an SMD resistor array consisting of 4 33 ohm resistors connected to the package pins like this. As you can see, the SMD type doesn't have a common pin. The internal resistors are connected independently and in parallel to the package pins like this. The SMD resistor arrays, just like through-hole types, the value of internal resistors are exactly the same and their value is indicated by the number written on the component. For example, this component says 330. This means we write 33 and add 0 zeros after it, meaning we don't add anything actually. So the value of the resistors inside this component is 33 ohms. So there are 4 resistors inside, each 33 ohms. Anyway, moving on, let's talk about another use for resistors that I know will be very helpful for beginners and will definitely open their eyes. I'm talking about using resistors for current measurement. For this, we need to revisit Ohm's law. We know that the voltage across a resistor is related to the current flowing through it and its resistance using Ohm's law. I mean this formula right here. Using this formula, if we know the voltage across a resistor and since we usually know the resistance, we can use this formula to measure the current flowing through the resistor. Anyway, up to this point, it seems pretty simple, right? It reminds me of when I was a beginner and measuring current was one of the most complicated and confusing things that I didn't even like dealing with. Of course, I knew Ohm's law and I knew that you could measure current using this law and a resistor, but I should also say that I always imagined the resistor that was supposed to measure the current was a simple resistor like this. This made it impossible for me to actually measure the current in practice. This is exactly where the line between theory and practice is drawn. Theory says to use a resistor to measure current, but practice says you can't use just any resistor to measure current because a resistor that can be used for current measurement has to have specific characteristics, and having specific characteristics and uses definitely means it has its own special name, right? Component number 2, shunt resistors. Shunt resistors are really awesome, but before we dive into them, I'd like to take a moment to thank our sponsor, PCBWay.com. PCBWay is your one-stop shop for high-quality PCB prototyping, assembly, and manufacturing. They offer fast turnaround times and competitive pricing and outstanding customer support. Whether you are a hobbyist working on a small project or a professional looking for large-scale production, PCBWay has you covered with services like multi-layer PCB fabrication, flexible PCBs, and even CNC machining and 3D printing. Check them out at the link in the description to PCBWay.com and bring your ideas to life with precision and quality. Anyway, we are getting back to the shunt resistors. Resistors that are used for current measurement are called shunt resistors and they have specific characteristics. For example, to avoid power loss or at least to have very minimal power loss, the resistance value must be very low. For instance, if you want to use a resistor of a few ohms, the power loss across the resistor will be huge. So, a resistor that is going to be used for current measurement must have a very low value, in the range of a few milliohms, for example. Having a low resistance also means that this resistor will probably be able to handle large current. Shunt resistors, just like any other component, can be through-hole like these or assembly like these. We usually place these resistors in current path, and by measuring the voltage across these resistors, we figure out how much current is flowing through these resistors and therefore the entire circuit that is in series with the resistor. Having a low resistance in milliohm range also has another advantage. For example, if you look here, the voltage across this shunt resistor will cause a voltage shortage across this load, and since the shunt resistor has very small value, the voltage drop across this shunt resistor will be very small, in the range of a few millivolts, for example, which is negligible in most applications. But that's not the whole story, because when the voltage across this shunt resistor is very low, it also makes measuring the voltage across this shunt resistor very difficult, even impossible with regular tools like microcontrollers ADC unit. Usually, to measure the voltage across a shunt resistor, which is very small, in the range of a few millivolts, for example, we have to amplify the voltage across this resistor before measuring it. And for this, in most cases, we have to use tools like Opamps. I'll skip over this topic here because this video isn't the place for those complex technical discussions. However, I've discussed this in detail in another video for those who are interested. I'll put the link to that video in the description. Anyway, let's move on to the next component, which is another type of resistors. Component number 3, ceramic cement power resistors. Ceramic cement power resistors are a type of resistors that can handle extremely high powers and currents. How much current they can handle is determined by their power rating and their resistance value. Here are some examples of ceramic cement power resistors. The resistance and power rating of each one is printed right on it. For example, this one is 1 ohm 10 watt resistor. If we do some calculations using Ohm's law formula and power equation, we can figure out the maximum voltage or current that this resistor can handle. For instance, take a look. This is a regular 560 ohm resistor with a quarter watt power rating, and this one is a ceramic cement 560 ohm resistor with a 10 watt power rating. Now, I'm going to use Ohm's law formula and the power equation to calculate the maximum voltage or current each one can handle. Now we can see that this regular resistor can handle a maximum voltage of 11.83 volts or maximum current of 21 milliamperes, but the ceramic cement power resistor with the same resistance can handle 74.8 volts or maximum current of 137 milliamperes. Ceramic cement power resistors are typically used when you need something that can withstand high currents or voltages. One common use is in simulating different kinds of loads. For example, some home appliance simulators that repair technicians use utilize these resistors. Let me give you an example. Let's say a technician is repairing the control board of a refrigerator. They might need to use ceramic cement power resistors to simulate something like the ventilation fan, so the fridge's board doesn't throw an error code saying ventilation isn't working, allowing the technician to test and repair other parts of the board. Okay, that's enough. Moving on. All the components we have looked at so far have had fixed values, but that doesn't mean that all resistors have fixed values. Component number 4, potentiometers. Potentiometers are 3-terminal components where resistance between the terminals depends on the physical or mechanical position of the component. This diagram shows the internal structure of a potentiometer, and here are few examples. These are sometimes called pots or volume controls, and these are sometimes called multi-turns. And this is an example of an SMD potentiometer. If you look closely, you can see the potentiometer's value printed on them. For example, this one says 10 kilo ohm, and this one says 223, which means 22 kilo ohm, just like how the values are written on the resistor arrays. The nominal resistance of a potentiometer is the resistance between the outer terminals, I mean pin 1 and 3, which is always constant and equal to the potentiometer's nominal resistance. Potentiometers essentially have a fixed resistance between the outer two terminals, which is the nominal resistance of the potentiometer. The middle pin is a wiper that slides along the resistive element between the outer terminals, which changes the resistance between the outer terminals and the middle terminal. If we call the resistance between the left pin and the middle pin R1 and the resistance between the middle pin and the right pin R2, the sum of R1 and R2 will always be equal to the potentiometer's nominal resistance. Basically, turning the wiper clockwise will make the R1 bigger and R2 smaller, and vice versa. If we turn the wiper counterclockwise, it will make the R1 smaller and R2 bigger. Potentiometers are pretty cool components, right? We have seen how they work and what they do. Now, you might be wondering where these components are used and how. That's a great question. The internal structure of a potentiometer gives them a really useful property. If we apply voltage to the outer terminals, the voltage at the middle pin will be a value between the voltage at the left pin and the voltage at the right pin, depending on the position of the wiper. For example, if I apply 0 volts and 5 volts to the outer terminals and measure the voltage at the middle pin with a multimeter, we can see that by turning the potentiometer shaft, the voltage at the middle pin can change and be adjusted from 0 volts to 5 volts. We can use this voltage as an input to a system to adjust certain parameters. For example, in my pocket size adjustable power supply, I have used 2 volume controls to adjust the output voltage. Potentiometers are variable resistors that work by mechanical changes the user makes to the shaft, but not all the variable resistors are mechanical. Many of them vary in resistance based on environmental parameters like ambient light, temperature, or other factors. I'm going to start with one of the most common, component number 5, LDR or light dependent resistors. This component you see here is an LDR or light dependent resistor, which is a variable resistor that changes resistance based on ambient light. The resistance between its 2 pins usually decreases as the ambient light increases. This component is called an LDR, a light dependent resistor. If I connect the 2 pins of this component to a multimeter and set the multimeter to resistance measurement mode, you can see that the multimeter shows a value. Right now, the resistance between the 2 pins is about 500 ohms. Now, if I block the light from hitting the LDR by putting my hand in front of it, you can see that the resistance between the 2 pins increases, and conversely, if I shine more light on it using a light source, you can see that the resistance between the 2 pins decreases. LDRs are used as light sensors, and you can build some really cool projects with them. One of the most famous projects you can make with an LDR is a photocell, which is used to turn on a light when it gets dark. For example, automatic lights that turn on by themselves at night are designed and built using an LDR and a simple supporting circuit. Another popular project is using this component to make electronic gifts, like a box that plays Happy Birthday song when someone opens it. Since it is always dark inside the box, when someone opens the lid, ambient light enters the box and activates the sensor. I say sensor. And that's right, an LDR is a sensor, but it is not the only sensor that works based on resistance, where the resistance between its 2 pins changes with the corresponding parameter. There are many other examples of these kinds of components available that you can use in your projects. For example, component number 6, humidity sensors. Humidity sensors, which come in many different types, mostly work based on resistance. Sensors like water sensors, rain sensors, air humidity sensors, or soil moisture sensors. These components you see here are all kinds of humidity sensors, but when someone says humidity sensor, they usually mean this module, which is an air humidity sensor. The actual sensor is right here, this gray component which has 2 pins, and its resistance between the 2 pins decreases as the air humidity increases. Let me remove this component from the module so we can examine it better. This component is the main part. It's the actual air humidity sensor. If I measure the resistance between the 2 pins of the sensor with a multimeter, you can see that it shows infinite resistance, meaning that the air humidity here is very low right now. Now, if I put the sensor above this cup of tea, we can see that the resistance decreases rapidly, and when I move the sensor away from the tea, the resistance between the 2 pins increases. Now, let's cut this plastic cover of the sensor with a craft knife to see what's inside. Okay, there's something like a printed circuit board inside, but you can't see much from here. Let's examine the sensor under a microscope. You can see that this component is nothing more than a simple PCB with a pattern that looks like electrodes etched onto it, which is covered with a special material. When the air humidity increases, a connection is created between these two electrodes, and as the humidity gets higher and higher, the connection between these two electrodes becomes stronger, and that's enough for us to use this component as a sensor. Other sensors have the exact same system. For example, the working principles of the soil moisture sensor is similar to the air humidity sensor. We have to insert the sensor into the soil and then measure the resistance between these two electrodes. As the soil moisture increases, the resistance between these two electrodes decreases, and as the soil moisture decreases, the resistance between these two electrodes increases. This is a rain sensor. We have to place this component in a location where if it rains, the raindrops will hit this component and cause the resistance between these two electrodes to decrease. Another example is this water sensor. We can place this water sensor inside the tank or glass, and by measuring the resistance between these two electrodes, we can determine the volume of liquid inside the glass or tank. The components we have looked at in this video are a few examples of different types of resistors, and the last two were examples of resistive sensors. Of course, resistive sensors aren't limited to these. You might remember that in the first episode, I introduced a component called an NTC thermistor, which is also a type of resistive sensor. In the next episode, I'm going to introduce you to a few more types of sensors which might not necessarily be resistive sensors, but they are very useful in their own right. Alright folks, this video is coming to an end after covering 6 useful components, and so far in this playlist, we have introduced and covered a total of 27 components. We will be covering even more components in the future episodes. So, if you haven't subscribed to my channel yet, now is the perfect time to subscribe and turn on the notification bell so you will be notified when the next videos are released. Thanks for sticking with me until the end of this video. Stay tuned for the next videos. Until the next video, good luck and take care.